Hi, I'm Thad Walker. Let me tell you about the research here at DW in my atom trainers research group. Right. I really have two kinds of experiments in my group. One is quantum information experiments, the collaboration with Professor Satman and Yavuz. And then the other experiments are ultrasensitive atomic sensors of one form or another. Our research is funded by National Science Foundation and also collaboration with Northrop Grumman Corporation, who partially sponsor our research and also collaborate with us. And so our students all get a uh, exposure to industrial research and development, which I think is kind of a unique opportunity. In our quantum information experiments, we trap atoms, collections of atoms, in two laser traps here. These atoms are 100 microkelvin or so, and then excite them using lasers to large principal quantum numbers around 100. And in that kind of situation, you can get very strong interactions between atoms, even though they're 10 microns apart. And we've shown that you can entangle atoms using these kind of processes. And we're trying to study how both how single atoms interact and also collections of atoms interact. That's been a theme of our experiments for the past few years. In our ultrasensitive measurements experiments, we're making ultrasensitive magnetometers. So they look like this, 10 centimeters or so, glass cell with lasers in it. The laser spectroscopy is such high quality now that we can measure precession of atomic electrons at the kind of 100 nanoradian kind of scale using these relatively simple devices. And then that translates into measuring magnetic fields that are in the range of femtotesla. And so example measurement is shown here a few years ago. We measured the heart signals of a 30-week fetus using this device that is shown over here. So we're interested in pushing the limits on how sensitive these magnetometers can be. And then we're also interested in ultrasensitive nuclear magnetic resonance. We have some new schemes for doing nuclear magnetic resonance involving novelties such as using pulsed bias magnetic fields. And in these fields, the nuclei do this little dance that you can see in the cartoon here, and here's signals that come out. So these are interests for navigation, in particular GPS denied navigation, but also, and this is where we're headed, is to search for potential axion-like dark matter like forces that can occur between nuclear spins and masses. And we have some limits on this in the past, but we're hoping the next few years to set up a new, very sensitive experiment to look for this kind of thing. Just a list of outcomes for alumni from my group. You can see a wide variety of things. People are at companies, they're at universities, they're at national labs, they've gone into the medical field, outreach, government advising, a wide variety of opportunities. Thank you for your interest, and give me a call or an email or whatever if you want to talk some more. Thanks.